Welcome to Introduction to Bioclimatic Design. I'm Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. In this video, we will discuss the overview of how bioclimatic design can shape better sustainable architecture design. This slide explains I equals to PAT framework. It expresses environment impact I as a function of P, population, A, affluence or consumption per person, and T, technology. It highlights the impact of anthropogenic emissions caused by human activities, lifestyle, and consumption levels on ecological footprints. Carbon emissions will continue to rise and 1.5 degrees Celsius. Global warming target will not be achievable unless we make significant changes. It prompts us to think about how better building design can reduce the impact by addressing these dimensions. This slide illustrates the idea of the ecological footprint for different impact scenarios. The term ecological footprint measures how much of Earth's resources we use compared to what the planet can renew. The graphs highlight how humanity's resource demand exceeded Earth's capacity, highlighted in the black line. If we keep the business as usual scenario highlighted in red, we need multiple Earths to sustain our current lifestyle. In other words, our buildings and cities contribute to using resources faster than they regenerate. Implementing rapid reduction strategies will move back within our planet's limits as highlighted in green. Therefore, adopting low-carbon practices is important since our built environments play an important role in saving land, energy, water, and materials. This slide gives us some staggering statistics from The New Carbon Architecture by Bruce King. It notes that by 2050, the world's population will increase by about 2.2 billion people. Furthermore, 2 out of 3 world population will live in cities. The growing population will need an additional 2 trillion square feet of new buildings by 2050. According to the reference book, this is equivalent to constructing a New York City every month for 35 years. This further emphasizes the need for proactive action in the built environment to prevent the world from reaching an irreversible 1.5 degrees Celsius global warming threshold. One of the issues with global warming is the socioeconomic impact, especially for the economically and geographically vulnerable residents. Vulnerable families around the world, for example, are being displaced due to climate-forced migration, such as food insecurity, sea level rise, flooding, extreme heat, and drought. The consequences of global warming are profound and multifaceted, from environmental to economic and to social equity. There are many books available on bioclimatic design. These books are recommended for those interested in exploring the topic further. Let's switch how traditional architecture is adapted to local climates. Building configurations and material selection are all influenced by local climates. The Indonesian traditional building features a steep thatch roof to shed heavy rains. Its building foundation is made of elevated logs to protect against flooding and keep the space dry through natural ventilation beneath the structure. The locally sourced thatch roof also helps keep the interior dry by breathing naturally. The Korean traditional building in the center has a sloped roof with extended eaves to protect the wooden column stable from rain and sun. The stone foundation supports wooden columns, and the overall wooden structure is further stabilized by structural weight from ceramic roofing tiles. The Iranian traditional building has a flat roof suitable for arid climates with less rainfall. The locally sourced earth brick or adobe helps with natural shading and ventilation. The thick walls and small windows further contribute to thermal modulation. We discussed the net zero design approach in the zero design videos. The net zero energy approach on the left consists of bioclimatic design, energy efficient systems, and renewable energy integration. The design goal is to reduce energy use through bioclimatic strategies and energy-efficient building service systems. This video focuses on bioclimatic design. Then, the on-site renewable energy system is integrated to support building operations. The net zero carbon approach on the right requires additional strategies beyond the net zero energy approach. Additional strategies include the use of renewable bio-based construction materials and the integration of vegetative systems, both of which offset carbon emissions from the building overall. The final performance goal is to design buildings that achieve both net zero energy and net zero carbon. For more information, refer to the additional videos indicated in the slide. Understanding energy end users is important to prioritize areas to be improved. The chart displayed breaks down energy consumption by end use. What stands out is that space heating is by far the biggest energy hog. It accounted for roughly 32% of the energy used, about 167 trillion BTUs. In comparison, other uses such as lighting, cooling, ventilation, etc., are smaller slices. The graphic emphasizes that in commercial buildings, heating is the dominant end use of energy. As designers or engineers, this tells us where the greatest potential for savings lies. If we can design buildings to heat more efficiently and need less heating through bioclimatic design, we reduce a building's energy footprint starting with heating. This slide shares another perspective on how climate impacts the energy end users. The data here shows that in cold and very cold climates, buildings consume much more heating energy per square foot than those in milder or hot climates. The data pattern will be opposite for cooling energy. This might seem obvious, but understanding energy use patterns is important for design. A sustainable building in a cold region should prioritize heating via features like high insulation, solar heating, and heat recovery, all aimed at reducing the heavy heating load. Meanwhile, in warm climates, cooling and shading is a primary focus via features like high-performance windows, shading devices, operable aperture, and landscaping. Climate affects building energy expenditures, and bioclimatic buildings must respond to those local climates. This slide explains different building types impacts different energy end users. For example, a restaurant will devote a large portion of its energy to cooking appliances and ventilation to handle all that kitchen heat and smoke in addition to cooling, whereas an inpatient hospital might have huge energy needs for ventilation and heating due to 24/7 operation and stricter indoor air requirements. A school might use a significant chunk on lighting and heating during daytime hours, but little on overnight usage. A bioclimatic design must consider the building's function and program to target the biggest energy drivers for that specific use. Takeaways. Highlight 1. Bioclimatic design is a fundamental step toward net zero building design strategies that utilize climate and site resources to create a healthy, energy-efficient built environment. 2. Bioclimatic design enhances occupant comfort, health, and well-being through natural ventilation, shading, daylighting, and moisture control. 3. Bioclimatic design minimizes the use of active building systems and reduces energy consumption in heating, cooling, ventilation, and lighting energy. 4. Bioclimatic design preserves natural resources while protecting surrounding ecosystems such as bodies of water, vegetation, and natural habitats. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Let's work together towards a sustainable future.